Well, hello, we were looking at cryptography. In particular, we were looking at block transposition ciphers using a permutation. So if I were to have a permutation, like, for example, sigma of, let's say, 1 equals 2, sigma of 2 equals 4, sigma of 3 equals 5, sigma of 4 equals 1, sigma of 5 equals 3. If I were to have this permutation, sometimes you'll see this written alternately. Here's an alternate notation for permutations. Sometimes you'll see these written like a matrix form. They'll write sigma, that's the permutation, equals, and you'll see it kind of like a matrix. So you take your domain, which consists of inputs 1, 2, 3, 4, and 5. Those are the inputs up top. 1, 2, 3, 4, and 5 in this case. And the outputs will go down below. So you got 2, 4, 5, 1, and 3. So the top row is the domain. The out row is the range of the output. So 1 goes to 2, 2 goes to 4, 3 goes to 5, 4 goes to 1, 5 goes to 3. So sometimes you'll see that. Yeah. Now, to find what's called an inverse permutation, the inverse permutation, we'll look at that. If I'm looking at the original notation, the idea is I got to find what's called sigma inverse. So previously the input was 1 and the output was 2. So basically I'm going to take this sigma right here, I'm going to pull it to the other side, and I'm going to get sigma inverse on the right side. So I'm going to get sigma inverse of 2 equals 1. And then we'll do this for the next one. Sigma, pull it to the right-hand side there. We're going to get sigma inverse of 4. So the output was 4. Now the input's 4. That's going to be equal to 2. Now the third one, we're going to pull the sigma to the right-hand side. We're going to have sigma inverse of 5 equals 3. The fourth one, we're going to pull the sigma to the right-hand side. We're going to get what? Sigma inverse of 1 equals 4. And for the last one, we're going to take the sigma, pull it to the right side. We're going to get sigma inverse of 3 equals 5. Now, what's the idea behind this? Well, the idea here is you have a domain and you have a range. And the domain is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the range is 1, 2, 3, 4, 5. So sigma is a function that sends 1 to 2, 2 to 4, 3 to 5, 4 to 1, and 5 to 3. So that would be sigma. The inverse sends things in the opposite direction. I'll use a purple color for the inverse. The inverse is going to have this purple color here. So sigma inverse is going to send everything backwards. So instead of 4 going to 1, 1's going to go to 4, 3's going to go to 5, 5's going to go to 3, 4's going to go to 2, and 2's going to go to 1. So that's sigma inverse. Now if you wanted the alternate notation, we call this what? Sigma inverse. I make a matrix, and I'd start off with 1, 2, 3, 4, 5 on top. And we work backwards. We work backwards. So let's look at my original matrix for sigma. Sigma here. So remember when the output was 1, the input was 4. So I'm looking at this right here. So I'm just going to swap those. So when I have 1 for my input, my output's going to be 4. Now let's also find 2 for an output. 2 for an output here. So now we're going to make 2 the input, and then the output would be 1. So we swap the input and the output. Let's find 3 as an output. That's here. So when the output's 3, the input was 5. So we're going to swap those and make the input 3, the output 5. And when the output is 4, that's the second column here, the input was 2. So now we're going to make the input 4 and the output 2 in the inverse function. And in the original permutation, when the output was 5, the input was 3. So now when the input is 5, the output will be 3. So this is your inverse permutation. 1 gets sent to 4, 2 gets sent to 1, 3 gets sent to 5, 4 gets sent to 2, and 5 gets sent to 3. Okay, just some permutation notation. Okay, let's do an exercise here. We want to decrypt something. Decrypt. You might hear it called decode the message. Let's say the code. Decrypt the code. NDOOXETEXFHDEXTAX RBE. Using the following permutation. Sigma of 1 is 2. Sigma of 2 is 4. Sigma of 3 is 5. Sigma of 4 is 1. And sigma of 5 is 3. So the first thing I got to do, I got to find the inverse permutation. What's the inverse permutation? But I want to undo encryption, so I want to decrypt. So let's see, sigma inverse. So here we have inputs in red in the original permutation, outputs in green. So when we have sigma of 1 equals 2, I'm going to take the sigma to the right-hand side. It becomes sigma inverse. I get sigma of 2 equals 1. For the next one, I'm going to take the sigma to the right-hand side. I'm going to get sigma inverse of 4 equals 2. And for the next one, I'm going to take the sigma to the right-hand side. I'm going to get sigma inverse of 5 equals 3. And for the fourth one, sigma of 4 equals 1, I'm going to take the sigma to the right side. It becomes sigma inverse of 1 equals 4. And for the last one, I got, let's see, sigma goes to the right side. I get sigma inverse of 3 equals 5. Now there's my inverse permutation. Now, I want to put this in order. I want to start with sigma inverse 1 equals 4, sigma inverse 2 equals 1, sigma inverse 3 equals 5, sigma inverse 4 equals 2, sigma inverse 5 equals 3. So I'm going to use that. And here is my code. It was what? NDOOX. We're going to break this up into blocks of 5. Why blocks of 5? Well, we have 5 inputs, right? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So this will be my first block of 5. And then I have what? E, T, E. I think I wrote too many T's. E, T, E, X, F. 1, 2, 3, 4, 5. It's another block of 5. Then we got H, T, E, X, T. I can write this pen. I don't know. H, D, E, X, T. It's another block of 5. 1, 2, 3, 4, 5. And we conclude with what? A, X, R, B. 1, 2, 3, 4, 5. So we got blocks of 5. 4 blocks of 5, right? There are 20 characters, which is a multiple of 5, so there are 4 blocks of 5. Now, we want to decrypt. So, we got 1, 2, 3, 4, 5 spaces in the first block, 1, 2, 3, 4, 5 spaces in the second block, 1, 2, 3, 4, 5 spaces in the third block, and 1, 2, 3, 4, 5 spaces in the fourth block. So our message is going to have 5 spaces on each block. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. All right. So what does our inverse permutation tell us to do? Well, it says to send 1 to 4. So we're going to take the n in the first place and send it to the fourth place. So n goes in the fourth place. Then it tells us to send 2 to 1. We're going to take the d in the second place and send it to the first place. So d in front. Tells us to send 3 to 5. So the O in the third place is going to go to the fifth place. Okay, and then sigma inverse 4 equals 2. We're going to take the fourth character, which is O, and send it to the second place. And then the last character, 5, is going to get sent to the third place. So X is going to get sent to the third place. All right, now we go into our second block. We got our first block. First block is D, O, X, and O. Now the second block, the first character gets sent to the fourth place. So E gets sent to the fourth place. T, the second character, gets sent to the first place. E, the third character, gets sent to the fifth place. X, the fourth character, gets sent to the second place. And F, the fifth character, gets sent to the third place. All right, so we got T, X, F, E, E for the second block. Now the third block of text, we have H, the first character, goes to the fourth place. D, the second character, goes to the first place. E, the third character, goes to the fifth place. X, the fourth character, goes to the second place. And T, the fifth character, goes to the third place. So for our third block of text, we have DX, THE. And our final block, we're going to start with A, the first character, that goes to the fourth place. X, the second character, goes to the first place. R, the third character, goes to the fifth place. B, the fourth character, goes to the second place. And E, the fifth character, goes to the third place. So try to make sense of that. We have D, O, X, and O, T, X, F, E, E, D, X, T, H, E, X, B, E, A, R. That's do not feed the bear. Right, spaces are filled in with X's. All right, so there we go. Decrypting, a transposition.